right. And okay. Yeah, okay, let's start. So thank you for participating in this colloquium, APSTP colloquium series. And today's speaker is Marc Henneaux from Belgium, the University Libre de Brussels and College de France. I don't know whether my pronunciation is good or not.
That's fine.
And Marc is also director of the International Solvay Institute. And actually, yeah, so Marc is studied at ULB 4 and also a lot of had a lot of prizes and honors and also grants, including Frankie Prize at 2000. Yeah, we are very happy to uh, have here as a colloquium speaker. Thank you so much for accepting our invitation. So today, Marc will give a talk about asymptotic symmetries in gauge theories with emphasis on gravity. Please.
Okay. Well, thank you very much for the invitation. I guess I should say good afternoon, although it's good morning on this side
Right.
of the planet. So indeed, I will talk about asymptotic symmetries in gauge theories with an emphasis on gravity. And I will start with, to motivate the question, I will start with a problem, which is a classic problem in general relativity, which is a problem of defining the energy. So it is well known that this is a subtle issue to provide a physical meaningful definition of the energy in general relativity. Now, why is it a subtle issue? Well, the problem is the following. We are told in courses of classical mechanics that the energy of a system is the value of the generator of time translations. But in general relativity, which time should we use? We know that general relativity is a theory which is invariant under general changes of coordinates, so which I will also call diffeomorphism, and these can involve arbitrary time reparametrizations, which means that in general, the time coordinate, the coordinate x0 in a coordinate system that you are using, in general, this time has no direct physical meaning, which means that if you want to ascribe a value to the generator of time translation, you have first to tell which time we should use. So what is the energy? When can we define the energy and how do we define it? Well, this problem is a classic problem in general relativity. It has been investigated by many people and it's well understood by now, and it's even in the classic textbooks. And the conclusion is the following, that in order to be able to, so I will actually quote that from the classic textbook by Misner, Thorne, and Wheeler. So here is what they say. The spacetime must be asymptotically flat, i.e. approach Minkowski space at large spatial distances, if there is to be any possibility of defining energy and angular momentum. Okay. Now, and they keep saying, so I continue quoting them, if spacetime is not flat at infinity, one must completely abandon the concept of total mass, momentum, and angular momentum of the gravitating sources. So here are these famous authors. And so why is it that spacetime has to be asymptotically flat if we want to define a meaningful energy? Why is it that we can then come with a precise expression for the energy which is physically meaningful? And again, I will quote the best authors. There is a very good paper a review paper on the issue by Ludwig Fadeev, and that was in 1982 in Soviet Physics. And here is what Fadeev says, which I will quote because it is very well expressed. So with the asymptotic Minkowskian structure, one can define a meaningful time translation, and now I quote, because the asymptotic condition that spacetime should be flat at large distances makes it possible to define a dynamic displacement in time as a displacement with respect to an observer far from the gravitating matter and to associate energy with the displacement. In contrast, in cosmological models, there is no natural time displacement. Well, that might depend on the cosmology, but in general, that is true, and accordingly, no energy concept. Or at least we have to refine the understanding. And so more generally, in the absence of boundaries or asymptotic region, there is difficulty in defining a meaningful time displacement and therefore a meaningful energy. So this is the conclusion to which these authors came. So to put it slightly differently, we see that in general relativity, there are diffeomorphisms that do not correspond to a mere redundancy in the description of the system, but they do have a physical meaning, a physical significance, and in particular space-time diffeomorphism, so change of coordinates, that go asymptotically to a translation in the asymptotic Minkowskian time, should be regarded as physical transformations, and they have a physical generator, the energy in that case. These are examples of asymptotic symmetries. So I went through that discussion of a classic problem in general relativity in order to arrive at the idea of asymptotic symmetry. So a space-time diffeomorphism, in the case of general relativity, that goes asymptotically to a translation in the asymptotic Minkowskian time is an example of an asymptotic symmetry. And I would like to understand better and to describe in precise terms the asymptotic symmetries and the generators of these asymptotic symmetries, which would be the corresponding conserved quantities. Now, to realize that not all diffeomorphisms correspond to redundancies in the description of the system, but that they can have a non-trivial physical significance, enable one to understand better also some paradoxical statements which are sometimes made. For instance, if you compare a star at rest and the gravitational field of a star at rest with the gravitational field of the same star but moving at velocity v, you could say that the two, and that's true, differ by a coordinate transformation. I mean, you just make a diffeomorphism that will approach a Lorentz boost with velocity v to go from one situation to the next. However, if you think that all diffeomorphisms correspond to redundancies in the description of the system, then you should say that these are identical situations. But it's clear that for an observer at infinity, a star which is not moving with respect to the observer, or a star that is moving with respect to the observer, is a different physical situation. And the point, and now that we can formulate it more precisely, is that the diffeomorphism that connects the two situations is asymptotically a Lorentz boost, indeed, and a Lorentz boost does not go to the identity at infinity. It has a non-trivial action at infinity. And so by looking at how things behave at infinity, you can distinguish between physically relevant coordinate transformations and mere gauge transformations that you can that do not change the physical situation. Another question which also could be phrased in a somewhat paradoxical way, but now can be understood if we realize that we should make a distinction between diffeomorphisms that have a trivial action at infinity and the diffeomorphisms that have a non-trivial action at infinity, is a concept of observables. Now, observables, sometimes it is said that in a gauge theory, the only observables are the quantities that are invariant under all gauge transformations. And so in gravity, these would be the quantities which are invariant under all diffeomorphisms. But if you look at the energy, or the linear momentum, or the angular momentum, you can change them by a diffeomorphism, namely a diffeomorphism that go to a non-trivial Poincaré transformation at infinity. At infinity, we can talk about Poincaré transformations because it's asymptotically flat. And the group of symmetries of flat spaces, as we know, the Poincaré group. So if I look now at a diffeomorphism that goes to a non-trivial Poincaré transformation at infinity, it will change the energy, the linear momentum. They transform just like these quantities transform under Poincaré transformations. So they are not invariant under all diffeomorphism. Does that mean that they are not observables? No, because actually the only condition one should impose on observables is that they should be invariant under all diffeomorphisms that go to the identity at infinity. And that's the only requirement that it is legitimate to impose. So we see that there is a very important distinction to be made between diffeomorphism or coordinate transformations that go to the identity at infinity. Now, these are really the true gauge transformations, and the ones that do not go to the identity at infinity, they have a physical significance. Okay, so I took the explicit example of gravity to illustrate that point, but these considerations are valid for general gauge theories. It's also true for electromagnetism, it's true for Yang-Mills, it's true, as we just saw, for gravity, for supergravity. We should make a distinction between different types of gauge symmetries in all these cases. The gauge symmetries, and I will use that terminology because I think it's a very good terminology. The gauge symmetries can be proper, so proper gauge symmetries. That's when they correspond to a redundancy in the description of the system. So in the case of gravity, this would be the diffeomorphisms that go to the identity at infinity. Or they can be improper, in which case they have a non-trivial physical action. In the case of gravities, it would be an asymptotic time translation or an asymptotic Lorentz boost, etc. Now, improper gauge symmetries are not redundancies in the description of the system, and they provide a lot of useful information about the physical system because they are physical transformations. In fact, in some cases, and I will illustrate that in the case of gravity, in the asymptotically flat context, in some cases, the improper gauge symmetries form an infinite dimensional algebra. And the fact that the theory should decompose into representations of that algebra give you a lot of constraints. Okay, so what is the distinction between proper and improper gauge symmetries? Well, we have an understanding of that in the case of gravity, but in general, we can phrase it as follows. All these transformations are gauge transformations, so they take the same form. So for instance, in the case of electromagnetism, you would change the electromagnetic potential by a gradient, both for proper and improper gauge symmetries. They take the same form. The distinction comes when there is a boundary or an asymptotic region. Well, that's technically it is really the same treatment. The boundary, in other words, can be at infinity, which is what I will assume for definiteness, and that's why I'm using the terms asymptotic symmetries. But if you have a boundary at finite distance, the same techniques are relevant. And so what makes the distinction between proper gauge symmetries and improper gauge symmetries is the behavior of the gauge parameter. So in the case of electromagnetism, it would be the behavior of that epsilon in the equation that gives a gauge transformation. It's the behavior of epsilon, more generally, of the gauge parameters at infinity, at the boundary, that makes a difference.
Can I ask a question?
Yes, of course, please.
Yes. So, is there any a definition for asymptotic region, or here the asymptotic is a certain there concrete definition or no? We usually use the term asymptotic, but in this context, can you define the term asymptotic in a specific way, or?
Yeah, so I will give a technique that is valid when there are many boundaries, and these boundaries can be at infinity, can be at finite distance. I will only focus on one boundary, and I will assume for definiteness that it is a boundary at infinity.
What
but
you're
you
saying
need to.
that, sorry, so when you say that asymptotic is just infinity far away, that's your definition, or?
Yeah, of course, that's a boundary at infinity, but well, I will not have the time to illustrate that, but you see, if you have, for instance, in 3 dimensions, Chern-Simons on a disk, the boundary is at a finite distance, you would have exactly the same techniques. You would need to put boundary conditions on the boundary when there is a boundary,
Yes.
okay? Then you will look at the gauge transformations that have zero action on the boundary. These would be the proper gauge transformations, but they would be also gauge transformations that have a non-trivial action at the boundary. And actually that could be, they could generate a Kac-Moody algebra or something like that, but which might be an infinite dimensional algebra. And these would be improper gauge transformations with non-vanishing charges, and you would have non-trivial representations of that algebra in the quantum theory. While the proper gauge symmetries are always trivially realized in the quantum theories, physical state should be invariant under proper gauge transformations, but they do not need to be invariant under improper gauge ones. They can form non-trivial representations. And this is really an important distinction for that reason. I'm not sure I replied to the question, but
it's related.
maybe okay. So, well, I will make things more precise, at least in the asymptotic context, but maybe I will try, if I think about that, to always say what you should do with the boundaries at a finite distance. Also, I will do it explicitly in the asymptotically flat context, but that could also apply to the asymptotic anti-de Sitter context. It's just the boundary conditions that will be different. But let me proceed, and you can, in any case, questions are welcome, and you can interrupt me at any time. Okay, and anyone. Okay, so so far I have been rather general, and I will be very precise, and I will, in the next slide, okay? Because actually, one way to be very precise is through the Hamiltonian formalism, because there is a very clear distinction that you can make between proper and improper gauge symmetries. I will come back to that in more detail, but let me flash the idea now. Gauge systems, and this goes back to Dirac, are characterized by constraints. When you go to the Hamiltonian formulation, there are constraints. And the constraints, well, related to the fact that there is a gauge invariance, are first class. And it turns out that the proper gauge symmetries, if you write the Hamiltonian generator, so they are canonical transformations, they have a generator. Well, the generator of the proper gauge symmetries are proportional to the constraints, and they vanish, therefore, when the constraints hold. While the generator of improper gauge symmetries have non-vanishing generators. In fact, as we will see in the next slides, the generator is also a linear combination of the constraint, but it has to be supplemented by a surface term, and that surface term is non-zero for improper gauge symmetries. And so the value of the generator, even when the constraints hold, is not zero. And that's really the technical, precise distinction between proper and improper gauge symmetries. Just look at the corresponding generators. If it is always zero for all configurations, that's a proper gauge symmetries. If it is not zero, it's not. But I will give some more general considerations and precise considerations on that in a second. Now, sometimes in the literature, people will call improper gauge transformations large gauge transformations because the corresponding gauge parameters usually do not vanish at the boundary. But I will use here the terminology proper versus improper. Okay, so this was the introduction. Okay, I still one more slide, I guess. As I said, yes, because the improper gauge transformations are have a true physical meaning and importance. They provide a lot of information on the system, and if it's infinite dimensional, and we know many situations where it is infinite dimensional, then they provide a lot of useful information and constraints on the quantum theory, for instance. So what I would like to do in my lecture here today is to review general properties of asymptotic symmetries. And in order to be concrete, I will use gravity as the main example, but I will try to phrase the concepts and the ideas in in a general language applicable to all gauge theories. Now, I would say that the case of gravity is particularly important because it has been argued that in the case of gravity, the only symmetries are gauge symmetries. There is no rigid symmetry. That has been argued from various contexts. But the gauge symmetries can be either proper or improper. So that's actually the only thing that they would be in the case of gravity. Okay, so, but before going to gravity, maybe I say a few general ideas, and then we'll take the concrete example of gravity in the asymptotically flat context, which is connected then with what Mismathon and Wheeler and Fadeev were saying, okay? Now, what are asymptotic? So in order to define the theory, well, the theory, you have an action which is gauge invariant, you have a boundary, there are boundary conditions. What are gauge asymptotic symmetries, proper or improper? Well, these would be gauge transformations, so that leave invariant the boundary conditions because the boundary conditions are given and you have to keep them fixed. But they are also, because they are gauge symmetries, they will leave the action invariant. But we request that the action is invariant only up to terms at the time boundaries. T1, so imagine that you are defining your action principle between two slices. So you give one initial Cauchy hypersurface at time T1, another initial, a final Cauchy hypersurface at time T2. You look at the action between these two time slices, okay, and we say an asymptotic gauge transformation that we are looking at should leave the action invariant up to terms at these time boundaries. So they will be canonical transformations if they leave the action invariant with well-defined generators. And as I told you already, but that was established in the general context by Dirac, if there is a gauge invariance in the system, there will be constraints, and the ones related to gauge invariance will be first class. And I will just denote them. We are in field theory by this letter G alpha, or curly G alpha, which, because we are in field theory, will be a function of the location in space, X. And the fact that they are first class, that was shown by Dirac, imply that if you compute the Poisson bracket, okay, now this symbol, the equal symbol deformed that I'm using, means that this is zero when the constraints hold. So it's not identically zero, it's not the zero function in phase space, because we are Hamiltonian here. So this will be a function of phase space, which is not identically zero, but it will define a surface in phase space, the constraint surface. And when you are on the constraint surface, two quantities which are equal on the constraint surface, I will use this symbol for equality. That means it's not an identity, it means that inequality modulo the constraints. And the constraints are equal to zero modulo the constraints, of course. So the first class property that if you compute the Poisson bracket of two constraints, it will be zero modulo the constraint. So that's the distinction made by Dirac between constraints, and the one relevant for gauge systems are first class. So gauge systems are described by constraint Hamiltonian systems, and well, that was one important contribution. I mean, he did so many things. One of them was the development of the Hamiltonian formalisms of gauge systems. Okay, now as I told you, the gauge transformations will have a canonical generator, a function of Q and P, such that when you compute the Poisson bracket of that function with anything, you will get the gauge transformations of that anything. Well, according to Dirac, and that's an important contribution to Dirac, or of Dirac as well, the canonical generators of the gauge transformations will be proportional to the constraint. So they will take the form of an integral over space of the constraints. Can you see this little hand on my screen? Yeah, okay. Of the constraints time the gauge parameters. Okay, so that will be, and remember the constraints are functions of Q and P. These are phase space functions. So when you take the bracket of anything with that expression, you will get the gauge transformation. I will give examples. And now it has been realized that if the gauge parameter epsilon does not go to 0 at infinity, you should add, and I will explicitly indicate how this is done, a surface term. And so the generator of the gauge transformation in the general case will be given by, in the bulk, a linear combination of the constraints with the gauge functions, parameters, plus a surface term. And I'm here in the asymptotic context, so I'm telling you it's on the two-sphere at infinity. If I was with a boundary at a finite distance, that would be an integral over the boundary. Okay, but that's exactly the same of an expression that will involve the gauge parameter at infinity or at a boundary in the case of a boundary at a finite distance. So that would be an integral of the boundary of some local expression involving the fields and the value of the gauge parameter at the boundary at infinity in our case. And the way you determine what this surface integral should be is that you ask, and I will write immediately an example, you ask that this generator has well-defined functional derivative, so it's a well-defined Hamiltonian generator. And that was a criterion very precisely spelled out and, I mean, given by Reggie and Teitelboim. So, for example, take electromagnetism. So the gauge transformation in electromagnetism are you add a gradient to the vector potential. So, first of all, in the Hamiltonian formalism, what are the dynamical variables, so the q's and the p's? Well, the q's are the component of the vector potential, ai, and the conjugate momenta, I denote them pi I, but actually these are the component of the electric field. So in electromagnetism, the electric field is conjugate in the Hamiltonian formulation to the vector potential. Now, as I told you, well, this is a gauge system, electromagnetism, that's one of the simplest, and there are then constraints. What are the constraints? Well, the constraint is Gauss's law. Well, I'm considering, for the purpose of illustration, free electromagnetism, so there is no charge. So there is a constraint that tells me that the divergence of the electric field is equal to 0. So this is indeed a non-trivial relation in phase space. I mean, the momentum pi I cannot be anything in phase space. It has to be constrained by Gauss's law, so that its divergence is equal to 0. And it turns out that this constraint, which is a constraint, is also at the same time the generator of a gauge transformation. So more precisely, the gauge, according to the general rules that I recalled, the generator of the gauge transformation will be Gauss's law sandwiched with the gauge parameter. So that's the bulk part. But then I will have to add a surface term. And what is this surface term? Well, that will be the asymptotic value on the sphere at infinity. So epsilon. So this is an integral at infinity. So only the value of epsilon at infinity is relevant, of the flux of pi I sandwiched with epsilon. And why should we add that term? Because if you compute the functional derivative of g, so if I vary g with respect to the canonical variables, well, here I have only pi I don't have any ai. So if I vary pi I will get from here, I will get minus di delta pi I. And from here, I will get delta pi I at infinity. But if I want to write the variation of g proportional to delta pi I, there is a missing I here, without any derivative, so that I can read the functional derivative of g with respect to pi I as a coefficient here, I need to make an integration by part to pass di on epsilon. And when I do that integration by part, I pick up a surface term, but that will be cancelled exactly by the surface term which I have from here. And so this surface term is added in order to cancel the surface terms that you pick up by integration by parts, so that the variation of G is always given by that expression with delta pi I. I'm sorry for the missing I. And that tells you that the variation of AI, because A is conjugate to pi, Q is conjugate to P, so you have to take the functional derivative of G with respect to pi to get the variation under a gauge transformation of AI. Well, it's just what you pick by integrating by parts, so this is di epsilon. You see, the functional derivative of G with respect to AI is di epsilon, to pi I, sorry, is di epsilon, the coefficient of delta pi I. And so indeed, we see that this expression is generating that gauge transformation even when epsilon is not zero at infinity. You see, if epsilon is zero at infinity, this is absent, and you don't have to worry about surface terms at infinity because they will be involving epsilon that is zero. But if epsilon is not zero, surface terms at infinity in general will not be zero, so you have to be careful, and this term has to be added. And so you find that this is the correct generator of gauge transformations in all cases, whether epsilon vanish at infinity or not. But the value of the gauge generator will reduce when the constraint hold to the surface term. And so if epsilon is not zero, you will pick up a term which involves the flux of the electric field at infinity, which is as it should. So you see, this is the general idea. I illustrate it in the case of electromagnetism. It's also true in all gauge systems. Okay. This is exactly what I said, but that's true as for all gauge systems. And the criterion is that you have a boundary term that you have to add to the generator, and whether it vanishes or not will tell you whether the transformation is proper or improper. So if it is equal to zero for all field configurations, because epsilon goes to zero at infinity, you call that a proper gauge transformation. It's a true redundancy in the description of the system. It's a gauge transformation as we have always been told that a gauge transformation is, and you have to quotient them. But if the boundary term does not vanish, then G of epsilon generates an improper gauge transformation. It has a non-vanishing value of its generator given by this boundary term. It has physical content, and you should not factor it out in the description of the physics. Okay.
May I ask something? Sorry.
Yes, sure.
Now you're discussing about gauge symmetries, right? At the classical level.
Yes.
Everything here is classical for the moment, right?
Yeah, I think everything will be classical up to the conclusions, even.
Okay. Because I was planning to ask about fermions, but they're
Fermions.
they're not included in this analysis necessarily.
Oh, but this is not a difficulty. Okay, because there is a pseudo-class, I don't know how to call it, let's say a classical description of fermions in terms of anti-commuting variables, and you can develop a Hamiltonian formalism for these anti-commuting variables. And so they would be, of course, you have to go to Grassmann algebras, but then they would appear in this classical description as well. So for instance, supergravity can be treated. I would have constraints which are fermionic, describing the local supersymmetry transformations. And depending on whether the fermionic parameter goes to zero at infinity, that's a statement I can make also for anti-commuting variables or not. I will need to add a surface term to the generator. So what I'm saying here will hold for if you adopt this classical, well, between quotation marks, description of fermions in terms of variables living in a Grassmann algebra. So from that point of view, the concepts are exactly the same.
Yeah, but the reason I'm asking is because I have in mind, for example, if you have fermions or chiral fermions, you may have in this symmetry anomalies. So in this case, you cannot apply all this procedure, right?
Well, if you have a gauge anomaly, but then that means that the theory is sick. So indeed, but okay, I will not. I agree with you that if the first class property is not preserved quantum mechanically, if the constraints do not you see, there might be anomalies at two different levels. You might have anomaly in the proper gauge symmetries, that the constraints are not going to be first class anymore. That is a signal in general of thickness, and you want to avoid that. There might be anomalies in the algebra of the asymptotic symmetries of the physically relevant one. You might have central charges, etc. That's not a problem. That actually might be interesting. So for instance, well, one classic example is three-dimensional gravity in the asymptotically antidocitic case, okay? Where you have a central charge in the asymptotic symmetry generators, classical, which appears already then. So that I think is not a problem. So I would say that you have to distinguish where this anomalous term comes. If it's only in the improper gauge symmetries, well, I will talk about the algebra now. It's not a problem. If otherwise, it can be a problem indeed.
Okay, thank you.
But okay, so I will say already the classic, I think it's very important before going to quantum to really understand the structure at the classical level. And well, I have only one lecture, so I will emphasize the classical aspect here.
May I ask also a short question?
Yes?
Yeah, yes. So the boundary term of this gauge generator, that you just explained, and that you explained that we can identify them by just checking the closure of the algebra. So that should be somehow related to also the boundary term of the action, right?
Exactly. Okay. So I will discuss that in the context of gravity. So maybe you can come back with that question if it's not well covered when we go to gravity. Yeah, so, but you are right. I mean, you have to know what the action is.
Excuse me, one more detail. You are working in 4 dimensions precisely, right? Or this?
Well, I was writing expressions for 4 dimensions just for definiteness. But again, these considerations are very general. They hold in in any number of dimensions. Okay, so for instance, the case I was referring to, 3-dimensional gravity, that would be 2 + 1 dimension. So, but in 5 dimensions, you can also do the same. So it's just to have definite formulas that I was using 4 dimensions. And also in gravity, I will do it in 4 dimensions. Things can be done, but are different from what I will write in the other dimension. So it's not a critical restriction. Okay, so let me proceed. One can show, and that is indeed classical, that because the constraints are first class, the Poisson bracket of the generators of 2 asymptotic symmetries is also an asymptotic symmetry. And if you compute this algebra, you get the following schematic form, that the Poisson bracket of 2 proper gauge symmetry is a proper gauge symmetry. The Poisson bracket of a proper gauge symmetry with an improper gauge symmetry is a proper gauge symmetry, and 2 impropers can be a combination of both. But this means that the set of proper gauge symmetries form an ideal, and it's algebraically meaningful to take the quotient. And this is physically what we should do, because the proper gauge symmetries are the redundancy in the description of the system. And when you take the quotient of that algebra, that you obtain what people call the asymptotic symmetry algebra. So the asymptotic symmetry algebra is really the symmetry algebra of the improper gauge transformations. Now, what does it mean that you take the quotient? It means that you are identifying 2 generators of gauge transformations that differ by a proper gauge transformation, namely by a pure combination of constraints. So then this is what we are told. We should identify them, which means that the fact that they coincide, I mean, that you have this equality tells me that I should identify 2 gauge transformations when the gauge parameters have the same asymptotic behavior, but they might differ in the bulk. the behavior in the bulk of the gauge transformation is physically irrelevant. The only physics is in the asymptotic behavior. And so that's why the term asymptotic transformations, asymptotic symmetries is a good terminology, because in a sense that the asymptotic behavior is physically the only thing that matters in a gauge theory. The asymptotic behavior, or the behavior at the boundary, if the boundary is at finite distance of the gauge parameters, is physically the only thing that matters. And once you have taken the quotient, of course, the only remaining things are the improper gauge transformations, and you get some algebra of that type. And if you want to, well, this is a technical observation, but the fastest way to get this algebra is just because the only information which is physically interesting is in the surface term. You just compute the variation of the surface term. So if you compute the variation of the surface term in this generator under the improper gauge transformation generated by that generator, and you will get automatically the answer to this on what should be on the right-hand side of this algebra. Okay, so computing these Poisson brackets actually are extremely simple. Once you work modulo the constraints, you just look at the surface terms. Okay, now this algebra, well, an improper gauge transformation can be, it's not necessarily a linear combination of the improper gauge transformations. It might be a nonlinear algebra. It can be centrally extended, and we have examples where all these things happen, but that's okay, because actually the improper gauge generators form a Poisson manifold. Okay, so these are the general considerations, and I would like to make them concrete in the case of four-dimensional gravity. So since the question was asked, I'm taking four-dimensional gravity to have a specific example, which is rather rich and interesting and raises interesting questions indeed. But I could do it for other systems. I could do it for Yang-Mills or Chern-Simons theory, say on a disk, or a more complicated manifold in 2+1 dimensions. I could do it for anti-de Sitter gravity. I could do it for higher dimensions, supergravity. But let me take a very specific example. The ideas that I will express and the method that I will follow is really exemplative of the procedure for any gauge theory. But there is still one more important concept, observables. So the observables, they would be phase space functionals, functions of functionals. I mean, we are in field theory of the canonical variables that are invariant under proper gauge transformations, but they don't need to be invariant under improper gauge transformations. And so the invariance is that you should have a vanishing, because these are the generators of the proper gauge transformation. No surface, so just proportional to the constraint. This is the invariance condition, zero Poisson bracket, modulo the constraints. And because we have seen that the Poisson bracket of an improper gauge transformation with a proper gauge transformation was a proper gauge transformation, we immediately see that the generators of the improper gauge transformations are observables. And so in particular, the energy, the other Poincaré charges obey that condition, and they are observables, even though they are not invariant under improper gauge transformation, but that's fine.
So can I have a question?
Yes.
So if we include charged particle in this analysis, I mean, in U1 gated theory, for example, electron, but electron couples to U1 gauge field. And then if we just require physical observable, I mean, then electron field should commute with a Gauss constraint. Then this electron field should contain Coulomb cloud. So
yeah, exactly.
essentially becomes a non-local quantity.
Yeah.
So, but even this asymptotic symmetry still remains in the asymptotic infinity. Then, so can you achieve irreducible representation of Lorentz symmetry or Poincaré symmetry? I mean, and the Minkowski vacuum is unique in this situation.
No, the Minkowski, well, we know that we might have this angle-dependent U1 transformation. So I think things are more complicated, but indeed, a physical observables associated with the electron field will have to be dressed by a function of the electromagnetic field in order to satisfy this invariance under proper gauge transformation. So that's correct. And the structure at infinity is very subtle.
Mm-hmm.
But if you do it correctly and take into account these angle-dependent transformations, you can define, you have a Poincaré algebra.
Oh. But the Minkowski vacuum is uniquely defined or not?
No, it's not.
Not.
I mean, there
Right.
is a so-called
Then the textbook
boson,
length,
there are
I mean,
bosons. Sorry?
the textbook result is wrong because we just assume Minkowski vacuum is unique, and then we just
Well, we know that Fock
irreducible.
space is very
Yeah.
tricky in the case of interacting fields. See,
Well, but this U1 gauge field is common, but but still we can define, we should define irreducible representation of Lorentz symmetry. But if this U1 gauge field present, then still at asymptotic infinity we have this asymptotic symmetry. I mean, this is local symmetry. And then my question is, what is the corresponding irreducible representation for such case?
This goes beyond my talk, but I would refer to work like Faddeev and Kulish, and well, we know that if the rigorous formulation of interacting fields, especially in electromagnetism, because we have to dress these fields with the charge fields with the electromagnetic potential. I mean, we have these infrared difficulties, and Fock space is not quite the appropriate arena for discuss. I mean, this is not my work. I'm just referring to other people, but this has been looked at. I mean, how to dress the electron field in order to have something which is invariant. And this goes back to Dirac, who also asked this question, in order to have something which is indeed unobservable.
I see, okay. Thank
Maybe
you.
you can ask this question again. You see, at the end, if you want to have more information. Let me proceed with the general analysis. It's classical, but you will see, I think that classically it's already, there are already many subtles and interesting points that have to be understood.
Okay, thank you, yeah.
But so in particular, if we have, in the case of gravity, observables that transform non-trivially under improper diffeomorphism, we know that we cannot express them only in terms of the curvatures. And so in the case of electromagnetism, there would be observables that cannot be expressed solely in terms of the electromagnetic field, F mu nu. And these observables will depend on the boundary conditions. Okay, so let me go to a concrete example, BMS group in 4 dimensions. So it has been realized by the work of Bondi, Metzner, and Sachs at null infinity that the asymptotic group of gravity is infinite dimensional, and it was called by, because it was found by Bondi, Metzner, and Sachs, it's called the BMS group. Now, this group was discovered at null infinity. So what they did, they assumed some asymptotic form of the metric at null infinity, and they asked for the diffeomorphisms that were preserving this asymptotic form. They thought that they would get the Poincaré group because that was this asymptotic form somehow reflected the fact that the space was asymptotically flat. So they were expecting the Poincaré group, but they didn't get the Poincaré group. They got much more. They got an infinite dimensional group, the BMS group, which contains the Poincaré group as a subgroup. This was done at null infinity. And so people ask the question, how does it appear at spatial infinity? And I will tell you how it appears, and for that I will use centrally the action written in Hamiltonian form. Now, the action for gravity in Hamiltonian form was deduced, was worked out by Arnowitz, Deser, and Missner. So it's called the ADM action for that reason. And it reads in Hamiltonian form, well, it has a standard form of an action in Hamiltonian form, namely PQ dot minus H. So I have to tell you what are P's and Q, the P's and the Q's, and then I have to tell you what are the H, what is H. Okay. Now the P's and the Q's are the spatial component of the metric, Gij, and its conjugate momentum, which is related to the extrinsic curvature of the constant time hypersurfaces. So these are the phase space variables. And you see that they appear in the kinetic term of the Hamiltonian action as PQ dot. So this is the PQ dot part. Sometimes it's called the kinetic term in the Hamiltonian action, or it's related to the symplectic structure. Actually, it tells you that P is conjugate to Q. So pi ij in this case is conjugate to Gij. Okay, so this is PQ dot. And now this is H, but because we are in a theory which has a gauge symmetry, namely changes of coordinates, diffeomorphism, we have constraints. And these constraints are, well, we have actually 4 constraints per space point. One, which I have called H, which is a relatively complicated expression, is quadratic in the conjugate momenta. And then it has also a term that looks like a potential term involving the curvature of the spatial metric. So this is a function of Gij's and its derivatives only. This is a function of the conjugate momenta, quadratic, with coefficients that depend on the metric. To lower the indices, also there is the square root of G. Okay, so this is H. And H is multiplied by a Lagrange multiplier that tells me that when I vary this Lagrange multiplier, that I have a constraint, namely this expression should be equal to 0.
Excuse me.
Yes?
Yeah. So actually, as I understand, there is a SPI group at spatial infinity. So I'm wondering why you consider BMS symmetry at spatial infinity rather than SPI group.
Sorry?
So as I understand, there is a symmetry, asymptotic symmetry group, asymptotically flat space-time. At null infinity, that is the BMS, but at spatial infinity, SPI group.
Well, I will.
So
let me discuss the construction of the group. We'll see what comes out. So
okay, yeah.
You see, I want to have a dynamical representation of the group with canonical generators, and we will see that we get the BMS group, not anything. That's what we get, period. So, but let me show you, which is nice because it's exactly the same group as at null infinity. I mean, which no tension. The same theory is described by the same group, whether you look at null infinity or spatial infinity. But of course, you have to be precise about what you mean by symmetry. And I will follow the precise definition that I gave in terms of Hamiltonian generator, which is well defined. But so I have to define phase space and the action, and this is what I'm doing. But you can ask the question once I have done the construction.
Okay, thank you.
So I come with no prejudice here. I'm just telling you, this is the action. I will put boundary conditions, and then I will look what is the symmetry. And let's see what we get. So this is the Hamiltonian constraint, and then we have also constraints which are related to, so this is related really to diffeomorphism involving the time, if you go carefully through the connection. And this will be constraints related to diffeomorphisms that are spatial diffeomorphism. Sometimes it's called the Hamiltonian constraint. And this involves derivatives of the conjugate momenta to the metric. Okay, and when I vary the corresponding Lagrange multiplier, which is called the shift, that's called the lapse, I get that this should be equal to 0. And then there is a surface term that has to be added, and that will depend on the asymptotic form of Ni and N. And since I will discuss that in detail in the next slide, let me not write now this boundary term. But the boundary term is completely determined by the asymptotic form of Ni and N and the boundary conditions you impose on the metric and its conjugate momenta. Okay, so this derivation of the action was done by actually Dirac and independently Arnaud with Desner and Misner, and Regis Teitelbaum focused a lot on the boundary term to be added. Okay, now to complete the definition of phase space, I need to give you boundary conditions on the canonical variables. which are Gij and Πij in this case. And I should really stress that, and this was done again in the case of gravity by Fock in the context of defining the energy actually, and it's very eloquently said. So I will actually quote again Fock, that we need to put boundary conditions to specify the theory when there is a boundary. Okay. So the field equation and the boundary condition are connected, and you should not somehow only look at the field equations and forget about the boundary conditions, or vice versa. The two really come hand in hand in order to define the theory. Okay, so what are the boundary conditions that I should impose on the gravitational variables? Well, I want the boundary conditions such that the action is finite and invariant at least under Poincaré symmetries. I would like the boundary conditions that if I make a Poincaré transformation, that they should be invariant because I am in the asymptotically flat context. And then the Poincaré transformations will be canonical transformations. It turns out I will get more. That was not expected, but at least I want to have Poincaré transformations. Otherwise, I cannot qualify the situation as describing asymptotically flat metrics. Now, this puts strong and interesting restrictions, and let's proceed with the action I wrote to see what we get. Okay. Usually people say, let's assume that we have, since we have an asymptotically flat situation, we have asymptotic Minkowskian and so spatially Cartesian coordinates, and they assume that the metric will decay as 1 over r, like the Schwarzschild metric, or the Kerr metric, the metric we know. They go as 1 over r, and the extrinsic curvature, let's assume that it goes as 1 over r squared. Again, this is justified by looking at solutions, and you will find that if you take Kerr or Schwarzschild, it's trivially satisfied. If you take Schwarzschild and boost it to have a moving black hole, where you compute the resulting extrinsic curvature, it will be of order 1 over r squared. So these are boundary conditions which are nice, and which are Poincaré invariant, it can be checked, and which contain the known solutions.
Sorry,
However, yes?
may I ask? So in the case of black hole geometry, we have another boundary on the horizon, but it is not necessary to impose some boundary condition on the horizon?
No, it is. I mean, whenever you have, well, first of all, the horizon boundary, it's a bit tricky because it's it depends. I mean, if you have the eternal black hole, you have another asymptotic region. I mean, but sometimes one can try to treat the horizon indeed as a boundary. Then we need to put boundary conditions on the horizon, and we have to work out what would be the transformations preserving the horizon boundary conditions and the value of the generators. I think it's a bit tricky because strictly speaking, the horizon is not really a boundary, so it's a bit more subtle, but one can try to implement something like that. So, but let me develop the theory with one boundary by focusing only on the boundary at infinity. There might be other boundaries. They would need some treatment following the same lines of reasoning, but adapted
so
to
just
these
short
other boundaries.
comment. Then in the presence of horizon, then basically we have two kinds of asymptotic symmetries.
Yes, you would have, or even an eternal black hole. There are two asymptotic regions, and you could independently, yes. Or if you take even Chern-Simons with two, this is known. If you have Chern-Simons in 2 + 1 dimensions,
right.
you have not on a disk but on an annulus. Well, you would have one Kac-Moody algebra on each boundary.
I see. Okay,
yeah,
thank
so
you.
this is probably the simplest case where this can be seen. So okay, and there might be connection between the two. I mean, there might be global thing that the zero mode should be the same or things like that. But indeed, if there are many boundaries, you would have more than just one asymptotic or boundary symmetry. Okay, now let me come back to gravity in 4 dimensions. If you only impose that, which seems reasonable, it turns out that there is a difficulty from the point of view of the action. And where is the difficulty? If you look at the kinetic term in the action, it will have a logarithmic divergence, so it will not be finite. So my boundary conditions will not make me the action finite. Why is it so? This goes as 1 over r squared. This goes as 1 over r. So I have 1 over r cubed that I have to integrate over the volume, so which is r squared dr. So I get dr over r. This goes as dr over r. So I have to integrate dr over r. So clearly I will get a logarithmic divergence. And this is a problem if you take the action seriously, which is what I do. I want to have a finite action, classically. So one way to cure the problem is to, so that means what? That means that I have to strengthen the boundary conditions, but I don't want to strengthen them too much. I don't want to, for instance, you could say, oh, let's assume that the metric goes as 1 over r squared and the momentum 1 over r cubed. Now, clearly this will be finite, but you are excluding Schwarzschild. So you don't want to be too strict with your boundary conditions. You have to be flexible enough to accommodate the interesting physical solutions, but I have to be more restrictive because my action is not finite. And the way people have done that is to impose extra conditions which constrain the leading order of the metric and then the conjugate momentum. So this is the leading order, 1 over r. This is the leading order for the pi's, 1 over r squared. These would be function of the angles. Symbolically, I can write them as function of the unit normals. And I will ask this function to be, well, this is a requirement that people have imposed, that this leading order is invariant under the antipodal map of the sphere. So I'm taking the North Pole to the South Pole and vice versa. I mean, and any point is mapped onto its antipodal point. They ask it to be even and the extrinsic curvature to be odd. Okay, the leading term, the sub-leading term, we don't care. Now, you might say, is this sensible to impose? That was really done by Reggie and Teitelbaum in the work that I alluded to previously. Well, that's sensible because you can check that all the known solutions which are asymptotically flat obey this extra condition. So it's not a big price to impose them because they are fulfilled. And you can also check that they are Poincaré invariant. If you make an asymptotic Poincaré transformations, they will be preserved. So from that point of view, they are okay, but they are better than the previous ones because they solve the problem of the logarithmic divergence. Why do they solve it? If you go back to the expression here only the leading term will matter. I mean, that's what I was looking at. But you will be integrating over r, that's fine, but also over the angle, so over the sphere. But you will integrate over the sphere a function which is odd under the antipodal map because it will be the product of an odd function with an even function. So the coefficient of this logarithmic divergence will be equal to 0, the integral over the sphere of an odd function. And so that solves, that cures the problem of logarithmic divergence. Now, you may ask, once you have imposed these strict parity conditions,
can I ask you a question?
what is the asymptotic symmetry group? Okay, we look at the group of space-time diffeomorphism that preserve these asymptotic conditions, and you will find Poincaré, and that's all you find, in fact. They leave no room for the BMS group. And why is it so? Well, of course, that requires some work. So let me briefly, which I will not reproduce here, but so let me. There is a question?
Yeah. So this antipodal condition is a particular value only for 4 dimensions. Is that true?
Yeah, in higher dimensions, you don't have to impose it.
But do the solutions we know in higher dimensions still satisfy these, or is it an analog of this?
Yeah, of course, the decrease will be depend on the dimension because the elementary solution of the Laplacian will have a faster decay. So what
I meant antipodal parity.
Yeah, so in higher dimension, if you go back to here, so if I was in 5 dimension, 4 plus 1, this would go as 1 over r squared, this would go as 1 over r cubed. So you will gain 2 powers of 1 over r, but you will only integrate with 1 more r coming from the volume element. So this logarithmic divergence is absent. and you don't have to impose parity conditions.
Yeah, but still, do the solutions we know satisfy any parity condition like this? Because you said that's a consistency, and imposing this doesn't.
Actually, if you look at this Perry-Myers black hole solution, which I think are the most general ones we know, I think they obey in appropriate. Well, you can find a coordinate system in which they obey the parity conditions. That's a precise statement. I'm not sure that they give it in a coordinate system where this is fulfilled, but they can be made to fulfill the parity conditions.
Thank you.
Okay, so as I said, the effect about these boundary conditions is that they leave no room for the BMS group. To be more precise, let me tell you briefly how it goes. You look at the transformations that preserve the boundary conditions and which are gauge transformations. So because they are gauge diffeomorphisms, they will be generated by the constraints in the bulk. So they take this form with some vector field that parameterize the diffeomorphism, okay, plus a surface term, okay. And these vector fields, you can check that the boundary conditions will actually be invariant under arbitrary diffeomorphism that are of order 1 at infinity, like the translations. That would preserve the boundary conditions provided the vector field is odd under the antipodal map. More precisely, it can have a constant, which are the translations, plus some piece which is odd under the antipodal map. And because if you look now at the expression of the boundary term, which will give you the charges, you can find, but I'm not going to reproduce the technical details here, you can find that this odd condition under the antipodal map, which is necessary to preserve the parity condition, automatically implies that the corresponding surface term is equal to 0. So these are proper diffeomorphism, and the only improper ones are the Poincaré transformations. Now you might say, well, this is because we are at spatial infinity. We should not expect to have the same group as at null infinity, but that's a bit disturbing because this is after all gravity and you go from one to the other. I mean, but just by integrating equations of motion. So you should not, it would be very puzzling and it's a bit schizophrenic, I think, to have one symmetry in one description and another symmetry in another description for the same theory. So I believe it's a bit a tension, but since that tension can be solved, why not? So let me tell you that the problem that we find here, that there is no BMS group as people found at null infinity, is due to boundary conditions which are now too strict. So this is just what I explained. And so these strict parity conditions are too strong, and actually they eliminate the extra transformations which appear in the BMS group. So the BMS group is Poincaré, but then there is an enlargement of the translations by what people call the super translations, which are angle-dependent translations. And these strict parity conditions that we have imposed eliminate the super translations, and that's why we don't see them. You see, if you impose boundary conditions that do not leave the possibility to perform super translations, clearly you are not going to see them. So we must unfreeze in these boundary conditions, which are expressed in terms of quantities which are not gauge invariant. That's the tricky part. We have to unfreeze the non-trivial BMS transformation, and that can be done very easily. We will relax the parity conditions, not completely, because then we get back to this logarithmic divergence in the action. So we have to keep something to maintain finiteness of the action. So we are going to relax the boundary conditions with strict parity conditions by a super translation. So we are going to twist them by a diffeomorphism. So I will allow terms with the opposite parity, provided that there are terms generated by a diffeomorphism, which will be actually a super translation. So I will take for the metric, so this is an ugly and complicated expression, but the concepts are extremely simple. I will allow in the leading term the even component as before, which I have denoted Gij, but I will allow an extra term which is actually a term generated by a diffeomorphism. So it's not just any odd term that I will allow, but I will allow an odd term which is generated by a diffeomorphism. And since it's asymptotically flat, to leading order, which is the one I'm writing here, to leading order is just a linearized diffeomorphism. So it will be parameterized by some order 1 diffeomorphism, which actually, for consistency, has to take a very specific form. It has to be the gradient of an order R function, which I write like RU. The bar here is superfluous. So this is this function U, which is a function of the angle. And I can assume that everything which is of even parity I can absorb in Gij. So I can assume that Uij is purely odd, which means that U itself is purely odd. Okay? So this is complicated as an expression, but the idea is very simple. I'm just adding to this purely strictly even term an odd term, but not just any odd term, an odd term generated by a diffeomorphism of order 1. And this is what is a diffeomorphism of order 1 in this Hamiltonian description. And there is an extra condition that I'm not describing here. Okay, so this is the twist of the strict parity condition by the diffeomorphism. And for the momenta, I will do the same. But the transformation of the momenta under diffeomorphism is a bit more tedious. You have to go through the Hamiltonian and compute bracket to see what it is. But so in the end, this is what you get to leading order. I will allow a term which has the opposite parity, which is not odd, but which is not odd and generated by generated by a diffeomorphism. And this is its expression in Hamiltonian terms. So the expression is a bit complicated, but the idea is simple. I will twist my strictly odd term by a diffeomorphism term of the opposite parity. So the twist is not just anything, it has to be induced by a diffeomorphism, okay? Written in Hamiltonian form, this is what it gives. And so you see that this twisting is characterized by two functions of the angles, one odd and one even. And then you can repeat the analysis. You can show that this will preserve finiteness of the action. You can check that, so the action is finite. You will have a well-defined symplectic structure between the phase space. So you will have well-defined generators. You can check that they are invariant under Poincaré transformations, including boosts. But there is more. Indeed, with these relaxed boundary conditions, one finds that the asymptotic symmetries are now given by more general hypersurface deformations that are consistent with the twisting and with a non-vanishing twisting. And they are described by the following diffeomorphism, that this would be boost and spatial rotations. They blow up at infinity like R, but then there will be order 1 terms. And for the time translations, this order 1 terms is an even function, and this can be odd. Now, the zero modes of T and WR would describe ordinary translations, but there is more because we can have an arbitrary function of the angle. This is a unit normal. So function of the unit normal is the same as function of the angles. And so we find that these more general boundary conditions with a twist are invariant under more transformations. That's normal. We are more flexible with the boundary conditions, so we have more transformations preserving them. And these additional transformations are described by one even function on the sphere and one odd function on the sphere. And actually, these higher spherical harmonics will describe the super translations, and exactly the same super translations as in null infinity. So you can compute the generators of these symmetries. And they're given by linear combination of the constraints plus a boundary term. And you can compute the algebra of these generators, and you find that it's just indeed the BMS algebra, provided you identify, well, you find that it's in a different basis. We have here a basis in which we are splitting the super translations into an even part and an odd part, but they combine together to form a single function of the angles, which is precisely the supertranslation at null infinity. You can completely connect the two. It's just a change of basis in the description of the symmetry, but that's something that can always be done, of course. So there is complete agreement with the null infinity results. In other words, to repeat, if I take these twisted boundary conditions, so in which I have strict parity condition twisted by an order 1 diffeomorphism, and look at the corresponding group of asymptotic symmetries, I find that the group of improper gauge symmetries is just the BMS group found at null infinity, and I can even match. Okay, I can do the matching because we can integrate asymptotically the equations of motion and find that a BMS transformation at null infinity is indeed described at spatial infinity by this object here. So these Hamiltonian considerations perfectly apply to the context. Actually, there is some improvement about the null infinity analysis. People at null infinity assumed what they call peeling, that there was no logarithmic term in the expansion around null infinity. You can show that the symmetry here doesn't care about whether there are logarithmic terms at infinity or not. So we know that the symmetry is present even if you have what they call polylogarithmic terms at null infinity. And these terms, which were neglected but are generically present at null infinity, will not spoil the symmetry. Okay.
Can I ask something?
Yes.
Yeah, I'm not quite sure. How did you actually, did you have to guess the generalization of the parity condition somehow? How did you produce it? You have some kind of method
No, well,
generalizing?
Okay, I can tell you how we produced it. Well, as always, it's simpler. It's easier to explain after the fact. So we first proposed other boundary conditions, which were also BMS invariant, but they led to some difficulty with the matching. But the argument is the following. We are giving boundary conditions in terms of Gij and πij. And because Gij and πij are not gauge invariant, our boundary conditions implicitly will involve some form of gauge fixing. You see, when you will say inevitably, because you are expressing the gauge condition, the boundary conditions in terms of non-gauge invariant quantity. And so there is always a question that you should ask to yourself, am I fixing too much in the gauge sector? Because you see, we should allow as much gauge flexibility as possible when possible. And so we thought that maybe because you see, if you fix too much, you will freeze improper gauge symmetries, but you are not allowed to freeze improper gauge symmetries because they're physical content. So we just looked at how can we relax our boundary conditions by a gauge transformation that would still make the formalism consistent. That is the philosophy, and actually I will push it even further later. So maybe that will illustrate your question. You can come back to your question after I have illustrated, when I will talk about logarithmic supertranslations.
Sorry,
so let me continue because I think that time is running. Okay. Someone wanted to say something?
I have some small question. So after imposing this parity condition, what is the topology of asymptotic geometry?
Okay, so in this case, I'm assuming that that things are simple at infinity. Okay, in other words, I have really a two-sphere describing my spatial infinity times a time variable, so I have some sort of cylinder at spatial infinity.
But if we have S2 at the spatial infinity, but if you impose this antipodal identification, then it becomes RP2 instead of S2, right?
Yeah, okay. So I'm handling that by dealing with function on the sphere, which fulfill this parity condition. And since I'm twisting the parity condition by this thing with the opposite parity, I have actually to the two parity. So I think it's better to work on S2.
I see. Okay, thank you.
Okay, and I think also, you see, because this S2 does not live by itself. I mean, it is embedded in space. So space is really Euclidean space. So it's, even though the fields have obey some parity conditions, which can be of either type, you see, because they are of two types. So I think this is a way to tell that you are on the sphere. And they are connected with three-dimensional space.
Okay.
Okay, they are boundary of a region in three-dimensional space, so that it's S2. Okay, so let me continue because I think that time is flying. So I should say that even though I'm not going to talk too much about that because I wanted to emphasize a classical concept, this infinite dimensional symmetry, and now we know that it's really defined also at spatial on space-like hypersurfaces. It will be valid for the physical states, etc. Well, the physical importance of this infinite dimensional BMS group has been discovered and understood fully in the last decade through the pioneering work of Strominger. And for instance, he has shown that because you have a symmetry, you would have worded entities in quantum theory, and that leads to the soft theorems. That's a way to understand the soft theorems, actually, which is extremely elegant and powerful. The so-called memory effect, which is a classical effect in general relativity, which is a displacement of detector after the passage of gravitational waves. So that can be understood in terms of super translations. So all this has been developed and shows the physical importance of the BMS group. Okay, it's just not a mathematical artifact. It's something that has physical consequences, classically and quantum mechanically. And actually, the quantum implications of the BMS symmetry are still under research. It's an active field of research. That, of course, underlies a whole program of flat space holography. But I will not. I should say also that we have also soft theorems in electromagnetism, and there is this infinite dimensional U1 angle-dependent U1 symmetry at null infinity, at null and spatial infinity that can be exhibited and which is important. But there are still classical aspects that need to be understood, and that's what I want to emphasize in the remaining minutes. I think I have, what, 10 minutes? 5 minutes? So, well, you cut me when I need to be cut. Okay, so
it's okay. Please continue. Yeah.
So let me give you one example of a classical question that has come out recently. If I look at the structure of the BMS group, I already pointed out some aspects. You have the homogeneous Lorentz group, you have the familiar translations, and you have the pure super translations. Now, pure super translations, which are these higher spherical harmonics in the description in terms of function of the sphere, commute among themselves, and they will transform in some infinite dimensional non-trivial representation of the Lorentz group. So schematically, and it's a semi-direct product, so schematically, I can write the algebra as a semi-direct product of Lorentz, homogeneous Lorentz, with this infinite dimensional algebra containing translations and super translations. Okay, as I said, L equal to 0 and L equal 1 harmonics, these are the ordinary translations, but you have the pure super translations as well. Now, schematically, I would have the following structure then. If I denote the homogeneous Lorentz generators by MA, well, this is the homogeneous Lorentz algebra. These would be the translations, ordinary translations. They transform in the four-dimensional representation of the Lorentz algebra, the vector representation. But then I have the super translations, an infinite number of them, but I keep the index alpha. No, it runs over all the higher order spherical harmonics. We have some symbolically the following Poisson brackets that tells us that the TIs and the S alpha form a representation under the Lorentz group, which is infinite dimensional. Okay. So from this algebra, there are intriguing aspects which have been pointed out already in the very early days of the BMS group. with which people felt somehow uncomfortable, and which all come from the fact that there is no invariant Poincaré subalgebra. You see, there is no invariant way to select Lorentz. The TIs form an ideal. The four translations form an ideal. But if you want to recover Poincaré, you need to add homogeneous Lorentz transformations, and they don't form an ideal. So there is no unique way to select a Poincaré algebra. There is no intrinsically defined way to select a Poincaré algebra. And in particular, there is no intrinsically well-defined way to select the homogeneous Lorentz group and to select the rotations. And that is a bit annoying if you want to define the angular momentum. Because the angular momentum, if you look at again in this algebra, so the angular momentum would correspond to some components of the Lorentz homogeneous part here. You see that under that you can read this Poisson bracket in two different ways. You can say that this Poisson bracket tell me that the super translations transform under Lorentz transformations, which is fine. But if I read it the other way, it tells me that the Lorentz generators transform under super translations. You see, if I make a super translations, MA will transform this way. Now, this is the so-called angular momentum ambiguity, that the angular momentum will not be invariant under super translations. Now, it's not invariant under ordinary translations, and we understand that well. We know that the angular momentum transform if you change the point about which you compute the angular momentum, but there is a way to define an intrinsic angular momentum, for instance, in terms of the Casimir of the Poincaré algebra. But the angular momentum ambiguity due to super translations is much more harder to handle, and no one has been able to define some out of the algebra an intrinsic way to extract angular momentum. And that's important, for instance, if you want to compute the angular momentum carried by a gravitational wave, you would get an answer that depends on the super translations, and that might be uncomfortable. Okay. And so it turns out that you can solve that question, and that's somehow related to a question that was asked to me on how we got the boundary conditions, which is that given boundary conditions, it's always a good question to ask oneself whether these are the more general boundary conditions we can consider. Can we relax them further? Can we allow more diffeomorphism at infinity? Can we allow more improper gauge transformations at infinity that might have interesting physical context? And it turns out that because our boundary conditions are always implicitly freezing some gauge transformations. Now, if they freeze gauge transformations which are uncontrollable, that's fine. But if they are freezing interesting improper gauge transformations, that's not fine. You see, the strict parity conditions were too strong. So we have an example. But maybe we are still too strong. Can we unfreeze some of these gauge transformations that we are fixing? I don't know a systematic way to answer this question, but in the precise context of asymptotically flat space, it turns out that we can relax the boundary conditions by allowing diffeomorphism that blow up logarithmically at infinity. It might seem that this is too wild, will not be under control, but you can show that by giving specific form to these logarithmic super translations, as we call them, you can enlarge the boundary conditions, and you can then enlarge the asymptotic symmetries. And with these extra generators that we get, we can redefine the angular momentum, but they will involve these extra generators in a way that is free from the super translation ambiguities. So the puzzle that I mentioned, which doesn't seem to be related in any way to the asymptotic conditions that I impose, actually can be solved by enlarging the boundary conditions. So as you see, that's an example of how do we know that we have the good boundary conditions. In a sense, we never know, because maybe we are fixing too much, but it's a bit of an art to answer that question. And in that case, we know that it's possible to relax them in an interesting way, because that solves this problem or this puzzle. I don't know if I should call it puzzle problem, but of the angular momentum ambiguity. And it's interesting to point out that what we did at spatial infinity was also done, the expression for the new angular momentum were derived at null infinity, and they just match. Okay, so let me conclude, because indeed I have exhausted my 1 hour and a half. Okay, so it's time for conclusions. So we have seen that in gauge theory is formulated on space with boundaries, which can be at infinity. Improper gauge transformations play an important role. They provide a lot of non-trivial physical information on the system. Physical state will have to transform in representation of these asymptotic symmetry group, which can be non-trivial by opposition to proper gauge transformations that have to be represented trivially because it's a redundancy. And gravity in the asymptotically flat context provides a very interesting illustration of that, because in that case, the group of asymptotic symmetries is infinite dimensional. Now, in order to do all the computations, we have to supplement the action by boundary conditions, and it's only when we have boundary conditions that we can ask what are the proper or the propagate transformations, and we have a very specific Hamiltonian criterion in terms of the value of the generators, whether the surface term that you have to add is 0, in other words, you don't have to add a surface term, or not. Now, it's always useful, as I indicated, to relax as much as possible the boundary conditions when it is possible, of course, and that might show some symmetries that you may exhibit some symmetries that you did not anticipate and that have a useful content. I emphasize the classical aspects. That was I got a question almost at the beginning of my lecture about quantum, but sorry, I don't have time to say more about the quantum theory. But the classical aspects, I think, are interesting, and also by being very careful in terms of Hamiltonian, you can resolve some confusion, I think, which exists in the literature. Here we have very precise criterion and to what is proper, improper, what is a symmetry, what has to be gauged, etc. And also having a well-defined Hamiltonian formulation enables one. This I did not illustrate in this talk, but to use all the powerful tools of symplectic geometry, and so standard Hamiltonian theorems apply. Now, the quantum theory, as I said, is still under construction. This is flat space holography, which is an important field of research, but I do not have time to go over that. And with this, I will thank you. So thank you very much for the invitation again.
Thank you very much for all the details, the lecture, and is there any question from the audience?
So there was already a question during the lecture.
Yeah, that's right. Yeah.
Hello.
Yeah.
Can I ask a question? Yeah.
Yes.
Okay, please.
Hello. Can you hear, Mark? Yeah.
Yes. Hello.
Yeah. It was very beautiful lecture. Thank you. So I have two questions. Yeah. You said the improper gauge symmetry algebra. I mean, computation of it actually boils down to the commutator of boundary terms.
Yeah, the computation of the variation of the surface charge, in fact. You just compute how they transform.
So then I imagine that the commutator of momentum and the field variable involves delta function. But this delta function is a bulk delta function, not on surface. So I imagine there is a kind of some regularization.
No, really, well, you will find that the commutator you will get the Poincaré algebra. So not the delta, it's not a local thing. We have the global Poincaré charge, and you will get the global Poincaré algebra without delta function. Now, if you look at now the super translations, which involve the angle, indeed, you can either do it in terms of spherical harmonics expansion, and then you will get some discretized form of the algebra with ln(m), and so you will get some structure constants that will depend on the quantum numbers characterizing the spherical harmonics ln(m) and L prime m prime. Or indeed, you can rewrite that in terms of delta function, but that would be delta function on the sphere. Just you can view that as a change of basis from spherical harmonics to function on the sphere.
So there will be
But there will be no delta function in space. I mean, that's what I want to emphasize.
along the radial direction. There will be no.
Yeah, no delta r minus r prime in a sense. No.
Another question is when you relax this boundary condition at the end of your talk, does the action still remain finite?
Sorry?
When you relax
so I relax the boundary conditions.
Does the action remain still finite?
Yes, okay, that's why you have to do it so the action is finite because this is a very important criterion that we are imposing. We want the action finite, and the reason is that we want to have a finite symplectic structure, and that's determined by the kinetic term in the action PQ dot, and so indeed it is finite. Now, that means that we cannot just allow any logarithmic diffeomorphism. We need to put some extra conditions on the coefficient of the logarithmic diffeomorphism. So that you would have log r times some function of the angles in front, and these functions of the angle will be submitted to some extra conditions that I did not have time to spell out in my talk that will guarantee finiteness of the action. But that's a non-trivial computation, indeed. You are right.
Okay. Thank you. Yeah.
Excuse me, I also have 2 questions.
Yes?
So one is for asymptotically flat space-time, so we know there is a BMS groups at null infinity. But for gauge field, in the gauge field also at infinity we have enlarged symmetries, but the people does not say what is the name of the group. I'm not sure is there a group, so what?
Okay, so at least in the case of electromagnetism,
Yeah.
people call it angle-dependent U1 transformation because this is what they are. So it's true that it should have a name. In some formulation you can get some sort of Kac-Moody algebra, but a priori you get angle-dependent U1 transformation or angle-dependent gauge transformations. It looks very much like Kac-Moody, and actually, indeed, you get Kac-Moody in some formulation. If you, and you have even Virasoro if you allow more super rotations.
Okay, so in this case, for to find the algebra, you use the Hamiltonian formulations. Then you might be construct energy, right, from the Hamiltonian formulations. Then that energy is the same as the Bondi energy. Or Bondi formula.
It will be the same as the Bondi energy in the limit where the Bondi coordinate u goes to minus infinity. Okay, because then it's radiated, of course. But there is a matching of the conserved quantities, not only of the Bondi energy, but of the angular momentum as well. You can match, but of course match where null infinity meets spatial infinity. That's a way of talking, but that's when in the limit u goes to minus infinity.
Okay.
U being the Bondi time.
Okay.
Added time.
Okay, thank you.
Okay.
Yep, thank you.
Thank you.
Okay, so we had a lot of questions so far, so let's thank to Marco again.
Thank you very much.
Yeah, thank you very much.
Thank you.
Okay, goodbye then.
Bye.